We will now turn our attention to the issue of extensibility and some of the approaches that have been taken to achieve this goal. Historically, I should mention that there was interest in extensibility at least as far back as 1981 with the system that was developed at CMU called the Hydra operating system. The Hydra operating system provided kernel mechanisms for resource allocation. The key word is mechanisms, not policies, just mechanisms for resource allocation in the kernel. And it had a way of providing access to resources using a capability-based approach. The notion of capability has a special connotation in the operating system literature, and that is, it is an entity that can be passed from one to the other, cannot be forged, and can be verified. All of the things that you want in order to make sure that the system integrity is not compromised is enshrined in this abstract notion of capability. And as originally envisioned, capability was a heavyweight mechanism in terms of implementing it efficiently in an operating system. And because capability is a heavyweight mechanism in the Hydra operating system, resource managers were built as coarse-grained objects in order to reduce the border crossing overhead, because border crossing in the Hydra system would mean that you have to pass capability from one object to another and validate the capability for entering a particular object and so on. And for that reason, Hydra used coarse-grained objects to implement resource managers. That way, they can reduce the border crossing overhead. And implementing resource managers as coarse-grained objects also means that it limits the opportunities for customization and extensibility. In other words, the coarser you make these objects, the less opportunity you have for customizing the services, which is exactly the strike against monolithic kernel as well. So while in principle, Hydra had all the right ideas of providing minimal mechanisms in the kernel and having the resource managers implement policies, because the fundamental mechanism for accessing the resources was through this capability, which is a heavyweight abstract notion to implement efficiently. In practice, Hydra did not fully achieve its goal of extensibility. One of the most well-known extensible operating system of the early 90s was the Mach operating system from CMU. It was microkernel based, providing very limited mechanisms in the microkernel and implementing all the services that you expect from an operating system as server processes that run as normal user-level processes above the kernel. And clearly, with this microkernel-based approach, Mach achieved its goal of extensibility. So it focused on extensibility and portability. The key word is portability. And therein lies the rub. Performance took a backseat because Mach was very much focused on making the operating system portable across different architectures in addition to paying attention to extensibility. And this, unfortunately, gave a bad press for microkernel-based design because it focused on these twin goals of portability and extensibility, allowing performance to take a backseat. And since operating systems are generally so focused on performance, this design choice in Mach of supporting portability gave microkernel-based design a bad press. But later on, when we look at L3 approach to microkernel-based design, we will revisit the right way to build a microkernel-based design. But in this lesson, let's focus on Spin's approach to extensibility. So the key idea in Spin is to co-locate a minimal kernel with its extension in the same hardware address space and avoid the border crossing between the components of the kernel and the extensions of the kernel that are containing the specific services that the applications need. And this co-location also means that we avoid the border crossing, which we said is one of the biggest potentials for losing out on performance. But if we're going to co-locate the kernel and extensions in the same hardware address space, isn't that compromising on protection? Wasn't that the strike against the DOS-like structure that we talked about earlier? Well, the approach that Spin took was to rely on the characteristics of a strongly typed programming language so that the compiler can enforce the modularity that we need in order to give guarantees about the protection. So by using a strongly typed language, in the case of Spin, they used Modular 3, more on that in a minute, the kernel is able to provide well-defined interfaces. All of you may be quite familiar with declaring function prototypes in a header file and having the actual implementation of the procedures in other files in a large software project. This is the same idea that is now taken to the design of the operating system itself. After all, operating system is also a piece of software, a complex piece of software. And why not use a strongly typed language as the basis for building the operating system? That's the idea in the Spin approach. Now, what you get when you use a strongly typed language is that you cannot cheat. For instance, in a language like C, you can typecast pointers so that a given data structure can be viewed completely differently depending on what you need to get done at the moment. That's not possible with a strongly typed language. Data abstractions provided by the programming language, such as an object, serve as containers for logical protection domains. That is, we are no longer reliant on hardware address spaces to provide the protection between different services and the kernel. As I mentioned, the kernel provides only the interfaces, and these logical protection domains actually implement the functionality that is enshrined in those interface functions. And there can be several implementations of the interface functions, and that's where the flexibility comes in. Applications can dynamically bind to different implementations of the same interface functions, and that's how we get different instantiations of specific system components, getting you the flexibility that you want in constructing an operating system. Because we have co-located the kernel and the extension in the same hardware address space, we are making the extensions as cheap as a procedure call. So in a nutshell, what we've accomplished with the Spin approach to extensibility is we are riding on the characteristics of a strongly typed programming language that enforces strong typing and therefore allows the operating system designer to implement logical protection domains instead of relying on hardware address spaces. And consequently, we're making extensions as cheap as procedure calls.